The African savanna stretches endlessly under the burning sun. Dust drifts through tall grass, and across the horizon a herd begins to move. Black and white shapes ripple through the landscape. Zebras. At first glance, their stripes seem simple, just bold black lines painted across white fur. But for more than a century, scientists have asked the same question. Why? Why would evolution create such a strange pattern? It isn't camouflage. From far away, zebras are easy to spot. It isn't just decoration either. Nature rarely wastes energy on beauty alone. And yet every zebra carries a unique map of stripes. No two are the same. Look closely at a herd running together. Something strange happens. The patterns begin to merge, lines intersect, shapes ripple. Predators often hesitate. For a moment, the herd becomes visual chaos. But this is only the first layer of the mystery. Because when scientists started studying zebra stripes more closely, they began noticing something deeper, a pattern hidden inside the pattern. To understand it, we have to look much closer, not from far away, but from only a few centimeters. Under a microscope, zebra skin tells a different story. Hair follicles arrange themselves in precise formations. Melanin pigments appear in waves, cells communicate through chemical signals, and suddenly those simple black lines begin to look mathematical. In the 1950s, a brilliant mathematician named Alan Turing proposed something radical. He suggested that nature could generate patterns using simple chemical reactions. He called it a reaction-diffusion system. Two chemicals interact. One activates pigment, the other suppresses it. As they spread through growing tissue, they create repeating structures. Stripes, spots, ripples. It sounded almost unbelievable. But decades later, scientists began testing his idea. And what they found was astonishing. When computers simulated Turing's equations, they produced patterns nearly identical to zebra stripes. The same flowing curves, the same spacing, the same irregular variations, but zebras were only part of the story. Because the same hidden algorithm appears everywhere in nature, on fish, on shells, even in the ridges of sand dunes. Nature, it seemed, was running the same mathematical program again and again. But zebras added a twist. Because their stripes don't just follow the reaction-diffusion pattern. They adapt to the shape of the animal's body. Along the legs, stripes run vertically. Across the torso, they curve and bend. Around the neck, they twist like flowing rivers. It's as if the pattern is being stretched across a living canvas. To see how this happens, scientists studied zebra embryos. Before stripes appear, the skin is completely uniform. Then slowly, faint waves of pigment begin forming. Dark lines spread outward like ripples in water. Each stripe emerges from chemical signals spreading through growing tissue. But here is the fascinating part. Those signals respond to physical forces. Skin growth, body curvature, hair orientation. All of these factors guide the stripes as they develop. The result is something extraordinary. A pattern that follows both mathematics and anatomy. A biological algorithm adapting to a living shape. But the mystery didn't end there. Because zebra stripes do something else entirely unexpected. They manipulate heat. In the scorching African sun, black stripes absorb more heat than white ones. This creates the black stripes. Cooler air flows above the white. These microcurrents generate subtle air circulation, essentially creating a natural cooling system. But that's not the only advantage. Stripes also confuse biting flies. Experiments showed that horseflies struggle to land on striped surfaces. Their vision can't properly interpret the high contrast lines. The pattern disrupts their depth perception, which means fewer bites, fewer infections, greater survival. Suddenly, those simple stripes reveal layers of purpose, camouflage, insect defense, mathematical beauty. But the most astonishing discovery came from something unexpected: artificial intelligence. When researchers trained pattern recognition algorithms on zebra stripe images, the AI began detecting hidden structures humans had never noticed. Subtle wave frequencies, spacing ratios, repeating geometric relationships. It turns out zebra stripes follow statistical distributions similar to fluid turbulence. The same patterns seen in cloud formations, ocean currents, and swirling galaxies. In other words, the stripes on a zebra echo the mathematics of the universe, from chemical reactions in skin cells, to the physics of airflow, to the geometry of natural systems, all encoded in black and white lines. But perhaps the most beautiful part of this mystery is individuality. Every zebra's stripe pattern is unique, like a fingerprint. No two maps are the same, yet they are all generated by the same hidden rules, the same underlying algorithm, nature writing infinite variations of a single equation. So the next time you see a zebra standing quietly on the savannah, look closer. Those stripes are not random. They are the visible trace of invisible mathematics, a natural code written in living skin. And once you see the pattern, you realize something extraordinary. Nature isn't chaotic at all. It's quietly solving equations everywhere. In sand, in clouds, in animal fur, even in the stripes of a zebra moving across the golden grass, a living equation walking across the African plains. And perhaps the greatest mystery of all is how many more hidden patterns are still waiting to be discovered.